The two very important theorems in linear algebra are both related to diagonalization, not surprisingly. One you already have seen, it's the Jordan normal form, where it says in most cases you can diagonalize, but there are some cases where you can't because you don't have enough eigenvectors. In that case, instead of eigenvectors, you use generalized eigenvectors, and if you use the generalized eigenvectors, the result is that you have a matrix on the diagonal, but you may have ones right above a few of the repeated eigenvalues. So that's Jordan normal form. But the singular value decomposition is at first it seems too good to be true. So it says that for any matrix A is equal to U D V star, where U, V are unitary matrices, and D is a diagonal matrix. Okay. Yeah, it seems too good to be true, right? It's basically saying, oh, you can diagonalize any matrix. What's the catch?
Unitary matrices?
No, unitary is even better. Usually it's impossible. The catch is that it's no longer true that these two are the same. This V is no longer the U star. In the spectral theorem, I wrote UD U star, right? Now it's UD V star. So you choose different unitary matrices. But so you might think, okay, well, I guess it could be true, but then it's still very surprising because it turns out that when I say any matrix, I don't even require A to be a square matrix. You can even diagonalize a non-square matrix. So how does that work? You might think, like, that's really strange. If you have like 3 by 3 matrix, what is this theorem saying? It's saying the following. See, this is a 3 by 2 matrix, right? So if you have a 2 by 2 matrix times 2 by 2 matrix, and then 3 by 3 matrix, 3 by 2 matrix, no. 3. Oh no, sorry, this should be 3 by 2. Okay. Yeah, 3 by 3 matrix, okay. So if you have 3 by 3, 3 by 2, 3 by 2, 2 by 2, then matrix multiplication goes like this. If you multiply n by m and m by l, then these two must have the same dimension, or else multiplication is not defined. But if they have the same dimension, then the outcome will be a 3 by 2 matrix. So they kind of like dot product away, and then you get 3 by 2. But then you have a 3 by 2 and a 2 by 2 multiplied, and then 2 contracts, and now you have 3 by 2. So you do have a 3 by 2. So I guess this is a little misleading. When I say diagonal, this is what I really mean. I mean that there's a 3 by 3 unitary matrix U, and then there's a diagonal matrix where you have, usually people call this sigma 1 and sigma 2, and then 0, 0, 0, 0. And then you have a V star where V is a 2 by 2 matrix. So yes, diagonal matrix means that you have the diagonal elements that's possibly non-zero, and everything off diagonal has to be 0. That's what I mean by diagonal. But then, yeah, but then it's still possible. Once you allow these to be also called diagonal, you can even diagonalize a matrix that's not a square matrix. So in some sense, it's very strong. Not only it tells us that you can diagonalize any square matrix, you can even diagonalize any matrix. The catch is that these two are not necessarily the same. So if your goal is to take nth power of A, it's not going to be a very good thing, because when you have PA inverse, PAP inverse, this was nice because if you take the nth power, then writing this repeatedly cancels the P inverse and P, so you end up with P times A and P inverse. That was the reason why this kind of diagonalization was so powerful, and that's how what enables you to calculate matrix exponentials and all that. You can't use that. This can't be used for matrix exponential purposes, for example. Okay? But it still has its uses. All right. So a little more detail here. In general, what happens is that, as I wrote here, you get some unitary matrix U, and then you have sigma 1, sigma 2, sigma m, and then you may have 0, 0. And then depending on whether it has more rows than columns or more columns than the rows, you might have additional 0 here or maybe more zeros there. I'm not so sure. Could be this or that, okay? And then you have V star. So let's say you have more rows than columns, then this is what you get as the diagonal matrix. And in such a case, the diagonal entries of D are called singular values of A. Okay. And that's where the word singular comes from. Okay? So when we say singular value decomposition, you're decomposing a matrix so that it's some unitary transform, and then you have a diagonal transform and another unitary. And these are called, these are called singular values. Okay, so let's now try to prove this. Okay, so I now going to try to prove this, and the way we're going to prove it is by having the following lemma. Okay. So the idea is that, let me say the idea first. Okay, so idea is that if you have any matrix A, then A times A star is going to give you, if you take its star, or if you take the star is a complex conjugate and transpose, right? Then it's going to, because transpose flips these around, so you end up with A star appearing first and then A, these flip, okay? And then star is applied to each individual ones. But then transpose done twice cancels, complex conjugate done twice cancels, so star star cancels away. So you get A times A star. Oh wait, what is that? That's itself, right? So what did we just show? That A star is? Huh? No, not normal. That was when it commutes with its adjoint. This is self-adjoint, or another way, yes, that's true. Yeah. Or Hermitian. Or self-adjoint, okay? self-adjoint on the complex vector spaces. So we know that if you multiply A with A star, it's going to be Hermitian. So because it's Hermitian, now what you can do is you can take, you can use the spectral theorem. Okay? So let A star B equals to U times D U star. Since we just proved that this is Hermitian, right? Then since this is Hermitian, then its spectral theorem says you can write this as a unitary times diagonal and the previous unitary star. Okay, that's spectral theorem. And let V1 Vn, okay, be U. Okay. Oh, I just realized something. Let me switch these around, okay? So I wrote it for the other case, but it's still true. If I have the star in the first one, you get the same thing. Okay, yeah, see, that's what I want. All right. So now what I'm going to do is V1 through Vn are the columns of this unitary matrix U. And see, what does this mean? Then I need some more context added to this as well, just a minute. So if you have A star A equals to U D, U star is really U inverse because that's what it means to be unitary, right? So if you bring this U inverse to this other side, then here's what you get. You get A star A times U equals to UD. And if you write down what it means, this is vectors 1 through n. These are the column vectors of U, equals to the column vectors of U again, but then diagonal matrix has entries lambda 1 through lambda n, right? So what does that say about V1 through Vn? Each of these vectors are? Look, this times this gives you this times this, right? What does that mean? If you multiply this matrix out, then lambda 1 through 0, 0, 0 here, when this multiplies to this, it only multiplies to the first one, right? So the outcome is you have lambda 1 V1 as the first column, right? So what does that mean? If you have some matrix times V1 equals to lambda 1 V1, what does that mean?
Isn't that the trace?
No. Yes?
They have with the, I'm forgetting the word, like the unique
No. It's the eigenvector. Okay? V1 is an eigenvector of this matrix with lambda 1 as its eigenvalue. Okay? Lambda 1 as its eigenvalue. So what we are going to do is we're going to let V1 through Vn be the columns of U, and we're going to say sigma I squared is equal to lambda I. Okay. So for each of these eigenvalues, I'll take the square root and I'm going to call it, actually let's just say sigma I will be square roots of lambda I. Now that makes you a little nervous because although we know that Hermitian matrices have real eigenvalues, what if this is negative, right? but it turns out that these eigenvalues will always be positive. And that's because if A star AV, if you have this, is equal to lambda 1 times V, then if you apply inner product with V itself, then this can move over here as its adjoint, but adjoint of adjoint is itself. And lambda 1 can be pulled out, and you have lambda 1 times VV. But look, this is positive. That's also positive, or 0. Right? So lambda 1 has to be 0 or positive. So that means because each of lambdas are 0 or positive, this is okay. So this definition is okay. So that's something that you should check. All right, so once we define this, here's what I'm trying to do. Okay. Then, if ui's, okay, are A applied to Vi, 1 over sigma I, sorry. 1 over sigma I, A applied Vi, we have Ui Uj equals to 0 for I not equal to j, and Ui equals to 1. Okay. So that's the statement. Wow, it just took so much time just to explain the statement. So let's continue. So let's prove that. Okay, proof. Let's say you have Ui Uj. Just write down its definition. Ui is 1 over sigma I, A Vi. And then Uj is 1 over sigma j, A Vj. Okay? And then, well, these are both real, so although the second component should come out as a complex conjugate, it doesn't, the complex conjugate don't do anything to real numbers. So if I pull them out, they both become 1 over sigma I and 1 over sigma j. And AVI, AVJ. And now what I'm going to do is I'm going to move this A over here. So that gives you sigma I, sigma j. Now how do you move? How do you move an operator to the other side? You have to take the adjoint, A star. So you have A star applied to AVI, Vj. Oh, but I know something about this. What does this give you? I know that VI's are what? Eigenvectors of which one?
On the diagonal?
No, not the diagonal. It's this matrix. It's so since you have this and Vi is an eigenvector of this matrix, it must be lambda I Vi. Okay. And then let's move this out. So you have lambda I over sigma j, Vi Vj. Okay. U is unitary. That means, what does this give us if U is unitary?
1.
No, if I and j are different, what do you get? 0, right? If I and j are equal, what do we get? 1. Okay, that's what unitary means, right? You have an orthonormal basis. V1 through Vn form an orthonormal basis. So what happens is that this is going to be 0 if I and j are different. Oh, so this is already done, right? And then if I and j are the same, then this will be vi, which is 1. So you get lambda I over sigma I. But I and j are the same, so sigma I squared is what you get, right, with lambda I times 1. And then look at this. What does this say? Sigma I squared is lambda I, right? So these two are the same. So you get 1 if I and j are equal. So proof is actually quite simple once we can define the correct terms. Okay. So that's the proof. We prove this lemma, but then this immediately has the corollary of the SVD. Corollary is SVD because what we now do is oh, I should have named this as V. Sorry. That's what we have. Because then, if I name U as, so what we just proved is that U is now another unitary matrix. Okay. Now, there's something that I'm not being clear here also. The thing is, see, in the previous one when we had like 3 by 2, I said U has to be 3 by 3 and then diagonal is 3 by 2 and then the V is 2 by 2. Now if you have such a case, you indeed have a problem. Just defining UI as this is not going to give you all the basis vectors for this bigger space. You need a 3 by 3, right? So to make an identity matrix from like another basis vector A to A, you need 3 vectors to form a basis for this bigger space. So what I'm not showing you is that once you establish that at least for these cases you have orthogonal matrices, orthogonal basis, then okay, well this means actually orthonormal basis, but then it's not, if it doesn't form the basis, then you can just extend it with a bigger space, so add more vectors, and then you apply Gram-Schmidt. What is Gram-Schmidt again? If you have any basis, you can apply this Gram-Schmidt procedure to have an orthonormal basis, right? That was, yeah. So that's something that we did. So what you can do is you can extend this basis so that now you have actually U1 through UM. Notice that I'm not saying that N and M are the same. M could be bigger, okay? So that this is again unitary. Okay? So what that does is, look at what this is. If you have the original matrix A and you think about, so let's say V, curly V is the basis with V1 through Vn, and curly U is basis with U1 through Un. If you do that, then what you end up with is you do get a diagonal matrix, because look at what it's doing. We just showed that A times Vi gives you sigma I times Ui, right? So this simply means that if your input is with this, and your output basis is this, right? Then you get sigma 1, sigma 2, all the way to sigma m, and you get a diagonal matrix. You might have a 0 here or a 0 there. I guess it would have been much easier if we stuck with a square matrix, but I did want to mention that SVD works for even non-square matrices, okay? So you can have 0 here or there, but anyways, you get a diagonal matrix if you choose the right basis. Okay? And this really means, what is this? This is same as A in the usual standard basis. I'll call standard basis I. And then identity from basis B to I, and then V to I, sorry. And then identity from basis I to U. And it's hard to track which is which, but I think this will be your matrix U, and this will be the inverse of matrix V. But V is unitary, so the V inverse can be written as V star. So U with this being, sorry. This should be like that, and then this, okay. So with this, so this is V and this is U star. This should be the inverse one. And then if you multiply to the other side, then you get this as your conclusion, which is the SV before. Okay. So that last part was a little flimsy, but it should work out. If you actually do the work, it should work out. So this lemma immediately shows that the spectral theorem implies that any matrix can be written as a unitary times diagonal times its adjoint, V, another unitary adjoint. So that's SV. It's quite nice. So next time, well, next time is the exam, but after next time, after the exam, I will show you a PCA, because now with SVD we can show PCA, which is like one of the very effective ways to handle data. You can like take any complex data and then apply PCA, and suddenly you have less stuff to worry about. It's a very cool kind of way of looking at things. All right, that's all.